So, welcome everyone to the AI for Impact Assessment final presentations. We organized this challenge together with Metabolic, and we're very proud to present the final results today. Over the last 10 weeks, we worked on this challenge, and I think the results are quite interesting to share with you guys. We have three teams. I will briefly explain who we are as Fruit Punch AI for the people who don't know us yet. And for the rest, I'd like to say enjoy. I will do the challenge introduction real quick. Then you'll hear from our data enrichment team who worked on using large language models to create new features from our data set. We had a zero-shot team working on zero-shot techniques, basically prompt engineering GPT and other large language models. Then we had a supervised learning team who built classifiers. And let me admit some people quickly to the channel, to the meeting, for semi-automatic methods that we tried, and in the final words will be coming from Peter and Ben. So for everyone who doesn't know us, we are Fruit Punch AI. We are a global AI for good community, and we started this community because we believe that to solve humanity's greatest challenges, we need to educate AI engineers at scale with an ethical and sustainable mindset. And the way we do this is by organizing AI for good challenges that are gearing towards the sustainable development goals. We organize challenges in the area of, for example, wildlife, energy transition, but also environmental challenges, as this is also one of, together with Metabolic. So the problem that we're trying to solve here today is a problem that comes from the consultants from Metabolic. Metabolic is a company that works on impact assessments, among other things. And during these impact assessments, their consultants have to manually match company transactions to CPC classes, the central product classifications. And these CPC classes are more than 4,500 classes. So doing this by hand is a very intensive, time-intensive task, and can also be very prone to error. It's also something we could try to solve with natural language processing, or with AI in the broader sense. So that's why we're here today. Our team was divided into the three teams that I just mentioned: data enriching, zero-shot, and supervised learning. And they all tried their own approaches on solving this problem with AI. Over the 10 weeks, we worked with three groups, and we had 25 great participants who all participated for over in a combined effort of over 2,000 hours of engineering work. As I said, the goal was to build NLP models to classify customer product descriptions, to estimate their impact on the environment. By doing this, we can get a very broad understanding of a company's impact on the world. Basically by classifying each and every single transaction or product that they bring in or export. The challenge started on the 12th of June. With 2 weeks of education and research. After the first 2 weeks, we set out to build a roadmap for the challenge, which we presented during the midterm presentation. And after the midterm presentation, we had 6 more weeks to come up with a final solution for this challenge. Today, you are present at the final presentation. The teams will have 1 last week to come up with the report. But this is, basically the result of what we've been working on for the last 10 weeks. I don't want to take up too much of the time because the most interesting presentations will be coming from the sub-teams. So I would like to give the word to the data enrichment team.
All right, so my name is Bram Kals. I was part of the data enrichment team together with these great people that all have a different background. Some are students, some are professionals, first-timers, but we also have people that are participating in their 6th challenge already. We are located all over the world, and together with this team, we worked on enriching the data set. Before we go into depth, we give a little bit more of an introduction to the problem, to the challenge. So as said, we're doing this together with Metabolic. Metabolic is a company that strives to transition the global economy to a fundamentally sustainable state. And it does this through consultancy, research, and it builds software and ventures. And one of the softwares that it built is called Link. And Link is a product that assesses companies to help them understand the impact that they have on nature and identify nature-related risks across their supply chain. And in order to do this, clients need to provide data, specifically product data, and this data is then used to create, let's say, an assessment report. This data that is provided by the clients is classified into these CPC codes, Central Product Classification. The current model that they use is not able to match all the product descriptions to the CPC codes. So, for example, tomate, which is the correct spelling in Portuguese, is matched to tomatoes. Same for gorgonzola cheese powder, but for the other two, it was not able to match these CPC codes or to a CPC code. So the goal of this challenge is to train an AI model to classify the product descriptions into CPC or LCA classes that are eventually used in the software. Sub goals are enriching the data using large language models, which was part of our team. Then there's another sub goal, researching and trying zero-shot learning, which was part of the zero-shot learning team, building supervised models, supervised model team, and then together we needed to provide the consultants at Metabolic with a top 5 prediction scores. Now we'll hand over the screen to Vivek, who will go into depth about the data enrichment that we have done over the couple of weeks.
So hello, everyone. As Bram was mentioning, the text comes in different forms, and our goal was to estimate the life cycle assessment or perhaps the CPC code so that the team at Metabolic can better assess the environmental impact. So being part of the data enrichment team, our goal was to deliver a data set that other teams further down the line can hopefully rely on and do their further analysis, for example, zero-shot or supervised teams. So the onus was on us to, for example, pre-process, clean, and give them or deliver a good data set. As part of that, we observed that the pre-processing was hard because, especially given the text at times was either too short or they were spread across multiple columns. And sometimes we also observed that the text is multilingual, as Bram was mentioning. One text was in Portuguese, the other was in English, and so on and so forth. And also the text was sometimes ambiguous. Excuse me. And also sometimes it also had some contained proprietary information, for example, flavor codes or some artificial information that is unique to that brand or category that not necessarily we could not find it, for example, by Googling it. So given these were challenges, apart from that, we also observed that because of the IO or for some other reasons, that the CPC codes the final CPC codes that we got from the team Metabolic also especially sometimes lagged, leading or trailing zeros. So given a 4-digit CPC code that we found by reading a CSV into pandas, for example, we could not determine almost all the time, at least, that whether the given code was missing a zero either at the start or at the end, or is it just a 4-digit CPC code. So this was an important factor because we wanted this to be finalized so that we can basically further deliver a labeled data set, for example, for sheet 1 for the other teams to work on. So while attempting this, trying to fix this, we ended up creating a comprehensive data pipeline. The first stage was data pre-processing. So basically, this contained the simple 3 steps. For example, cleaning and transformation were not that complex. The cleaning part was just stripping off the extraneous spaces, and the transformative part contained converting everything to lowercase because some of the texts were straight. Everything was in uppercase, and everything was in lowercase. So there was no point maintaining different cases. So we simply converted them into lowercase, and we also expanded some known acronyms and abbreviations by simple regex operations that would further help down the line the LLMs so that they can properly create features. So where we come to the feature extraction part, where it's the job of the LLM, such as ChatGPT or any other LLM, to extract other text features based on the short text that we get as part of the client text. The second part was the deriving embeddings. So we have this UN taxonomy data, which had some title and explanatory note. So this for every given CPC code, we have what it means and what some description of it sometimes. So we derived embeddings by using those two columns, and also we created embeddings out of the text features that we extracted from the client text that we received, and we did a similarity search and we extracted top K results. And this is where I was mentioning, while attempting to fix this leading and trailing zeros, further with the help of Metabolic, we ended up doing zero-shot labeling as well, where the goal was to predict amongst these top K using an LLM the final prediction. And then that was the final prediction that we eventually delivered, along with the features and the text as well, and the top K matches. And finally, this is still work in progress, but we also have advanced schema validation checks as part of the pipeline, and also in workflow orchestration using Pandera and Prefect. So this is just a short example. So here we have two sheets for the data set that we have received. The green ones are the data columns, which we are guaranteed to be available at the inference time. The other columns are labeled white, where we did not use those columns because they are not guaranteed to be at inference time. And we only have target labels for sheet 1, which is the math CPC code, which we were also trying to fix as part of the zero-shot labeling. So, but the pipeline is generalizable to any sheet. For example, as you can see, this is sheet X, where the data column, the columns that are interesting and available for us so that we can make an inference can be spread across multiple columns, as I mentioned before. And then our goal was to eventually predict if like a given top 5 or top K CPC matches. So here, one of the first step was to basically, as I mentioned, cleaning the data set. Everything can be done in a couple of lines of code. Here, the raw data frame DF is basically the data frame that we get from Metabolic or from any other data set. This can be simply read as a CSV or Excel file. It can be read as data frame into Pandas, and the highlighted green columns are the data columns. We don't use column 3 or any other columns. We only use the green ones, for example. And then we end up creating separate columns, which are the cleaned versions of each column. We prepend that with clean underscore just to have that, just to track it. And also we append all the data sets that we are going to create to the existing one, so that for every given data point, we can track the whole transformation across the whole pipeline. So here, as you can see, for every column, we create a clean version. And then here you see the TRM is expanded to trimmed. This is basically some simple regex. And IQF, which stands for individually quick frozen, which is a term in the food processing industry, is not expanded intentionally because the job of the LLMs, they would further expand. The ChatGPT, for example, would expand it and then derive features for us. So once all their clean columns are, once we derive all these clean columns, we create another column, combined clean text, which combines all these clean columns into one single column. As you can see, they are separated by semicolons, and this column is the one that we are finally going to use to derive features. So here, for example, now we are going to the feature stage. Again, just a couple of lines of code to build the features. And then now the other columns don't matter. We are only interested in the combined clean text. So the clean text can have all the information from the cleaned versions, and then we derive using context prompt engineering, we derive some features for the text based on using ChatGPT. So here, as you can see, we have successfully, for example, detected the language and what that means, and some description under 75 words, for example, and then 5 or 6 keywords. So once we have these, we go to the embeddings phase. So this is where this is from here on, we are doing this, for example, to do this zero-shot labeling to fix the labels as such. So we have this prediction, source language, translation, description, keywords, and so we use description and keywords to create embeddings, because description contained the information from the other two columns as well. So we merge this column in a smarter way, taking off the CPC codes and etc., stripping off the CPC information before feeding them to a ChatGPT or any other LLM. So basically, we create an embedding using a sentence transformer model. So this is our query, and this we want to get top X matches for this query, right? So we have this CPC data, official UN CPC 2.1 data, where we have a title, we have a CPC code, we have a title, and then optionally, sometimes we also have explanatory note. So once we have this query, we also merge this embeddings, and then we get top 5 or top K matches here, and K can be arbitrary. For our use case, we went with 5, but it can be anything. So we have this top K matches, and then so now you have, for every given query, we have top 5, for example, CPC codes. And in our use case, we went ahead with 5-digit CPC codes so that we can do a fine-grained classification, and further on, depending on the convenience, you can choose to go higher level if you want. So later on, coming to the zero-shot prediction, as I mentioned, so we have this top K, we end up with the top K, and then we query. So basically, we know what the CPC code title and description is. So we feed that as a dictionary or something to a ChatGPT in a JSON format, and then we ask to pick the right one given the description. Pick a key that matches the description, for example, and the key, the value is what the ChatGPT or any other LLM uses to decide on the key. Once we have that, we deliver the final prediction. So this is the pipeline. So we did this on sheet 1 because we already have the target labels. So for sheet 1, this is the results we have gotten based on the recent revised labels from the Metabolic team. So the subclass, we are doing a fine-grained subclass classification. So basically we are predicting 5-digit CPC codes. So across the sheet 1 dataset, which is around 900 unique data points, 950 unique data points, we were obtaining an accuracy like 5-digit match of 59%. And then as you go higher up, the abstraction level increases. So you naturally would get a bit higher accuracy because you're basically generalizing but not doing fine-grained classification. And we also observed that 76% of the time, the final label is one of the top 5 predictions that we did. So that is assuring. So this means that the lower level accuracy can be further improved by perhaps using a better improved final context. Like, for example, we can use advanced GPT-4 model, for example, to pick up amongst those top 5 matches to further increase the accuracy scores that you're seeing here. And for sheet 2, we only have gotten 100 corrected label or 100 labels examples. So we did prediction, or we could only check how good our predictions are only on those 100 examples. So these are the results, but you can see they follow the same pattern. Again, 73% of the time they are in the top K. But of course, we didn't have any baseline results to compare them with because maybe the other teams or Metabolic team can further comment on this. But based on just pure zero-shot labeling, we didn't use the predictions that the Metabolic team gave us at any time during the prediction. So we only used it to compare here. So that's what zero-shot learning does. And finally, now that we have those results, we worked on creating this. For example, everything was in notebooks, and then we ported them to scripts. And as you can see, everything was in everything can be done in a short couple of lines of code. But we went ahead and also created a advanced, for example, data validation checks. For example, here, as you can see, this is a small snippet that does everything in one go, like cleaning, pre-processing, extracting transformation features, and doing the zero-shot labeling, and also storing all the time, every time necessary. Everything can be done in one simple, for example, by calling this one line, and you give the raw data that I mentioned before, and then you end up with 3 different data sets where every data set above contains every data set below contains all the information above. So you end up with a clean data set first, and then you do the features, and you append those, again, as I mentioned, row-wise to the previous data set. So in the end, you would end up with 3 data sets at 3 different abstraction levels. Of course, it is prone to error. And we also, as mentioned, the CPC codes sometimes are actually loaded as integers, so you have to do some validation. That's where, for example, Pandera and Prefect comes. Like, for example, with Pandera, we do the data validation checks before storing or loading the dataset so that we can be assured that the data that we are loading or storing have the same schema that we expect it to be. And once that is done, we also use the Prefect, for example, workflow orchestration, so that everything can be run as a pipeline, as you can see here. You can track those. You can run multiple runs, just like, for example, data cyclic graphs that ETL data engineers use. So you can run multiple runs, and also you can go through each run, and you can also go through the logs for each and how each stage is getting progressed. So this is all. And in summary, we have finally extracted, cleaned, and transformed the features. We were able to derive embeddings for CPC taxonomies and also the input features. And using the cosine embedding similarity searches, we were able to successfully extract the top K matches given the query. And then amongst those top K catches, we were predicting using, an LLM, we were able to do the zero-shot prediction. And then finally, we also were validating and transform this into a pipeline that we can orchestrate at different various abstraction levels. Yep, this is it. Thanks, and we're up for questions.
I have a question. Firstly, very impressive. You've come along quite far, not only the data engineering, but also the several steps after with the zero-shot learning and even the full Prefect pipeline. So that's really cool. So this question, I think you might have answered in any of the intermediate meetings, that you ended up doing a top 5 prediction, right? Have you tested with higher amounts of predictions, and were the results better then? And the main reason that I'm asking is because you mentioned as well that this part of the prediction is likely the reason that the accuracy might be a bit lower, as in if that prediction would be more accurate, then the next prediction would also be more accurate. And by increasing the amount of labels, then also ChatGPT or any other large language model would have more options basically to select from. So I'm curious whether you tried that and what's your view on that?
We tried top 3 and top 2, but sometimes like almost in our observation 87% of the time at least the prediction falls within the top 3, and just to be sure and to cover a bit wider area we tried only until top 5. But of course this is arbitrary and we can set it as a parameter and then give it. But we also observed that for example, the more key value pairs that we give to the ChatGPT, at least 3.5, the less likely it is to arrive at a good answer, because maybe it is getting confusing or something, or perhaps we need a bit more testing. But we didn't test beyond 5 at the moment.
Okay, that's interesting. So the insight that you mentioned, that it is actually better with less options than instead of...
But not too little as well. Yeah.
Well, I would think that such a large model would be able to handle, well, let's say 10 or maybe 25 options. But thanks.
Maybe, yeah. Or maybe it ultimately has to do with prompt engineering, I think. Or maybe we have to improve the context to handle it better, I think.
Okay, cool. Thanks.
Justin, you have a question?
Yeah, really interesting work. My question is about the CPC labels themselves. It wasn't clear to me whether you pass them through the same pipeline as the client text, or you just try to match you only enhance the client text and match them to the simple labels.
Exactly, the second one. Throughout the text feature engineering part and the content prompt engineering part, we never let a ChatGPT or any other LLM knew that we were dealing with CPC taxonomies, because it has been observed that they hallucinate a lot. Given a description, they could not predict a CPC code, or given a CPC code, they could not give a description. So we stripped off the CPC information, but still kept CPC digits, the information, but we still kept the text. And then ultimately, during the zero shot, we just used the CPC codes as key, and the ChatGPT just naively picked the key. Had it been A, B, C, D, it could have picked any of those. So we just replaced those A, B, C, D, E with, for example, keys. Yes, Ben.
Hi. If I look angry, that's the sun. Photon. So I'm not angry. I'm super happy with what you have presented. Super cool. What I'm curious about is, the enrichment. You take an approach where the original text is mapped to some other text. So that's enrichment, of course, and that's probably very valuable. But have you considered or run experiments where you just take the embeddings themselves, because the embeddings of the original text might contain the same kind of information that is used to generate the text that you in the end use as enriched data, if you know what I mean. So have you run experiments where you verify, where you compare just raw embeddings of the original text versus the one where you take multiple steps to come to this, to a numerical representation?
No, we did not do that. But at least one of our team members at the moment are trying to find out the embeddings, like for example, the query embedding versus the top K matches, and for example, find out how cosine, for example, any similarity metric, for example, cosine, how similar they are. But we did not, at least at the moment, not that I'm aware of, created embeddings from the raw text itself, because some of them are sometimes there was too much text to process. But of course, we didn't do it yet.
Yeah,
maybe.
Yeah, interesting. Yeah, really curious. Whether including scraped data, you query, or you find the corresponding page on Wikipedia, and then you create an embedding for that. Whether that can compete with the embeddings that OpenAI generates, or whether that's basically already in there, right? So just
perhaps
curious about the inner workings and what's in there semantically. But yeah, thanks.
Sure. Yeah, Rosina.
Thanks, Vivek. It was super interesting to see you. I have a question about the input data, because in the example that you showed, the first two were really sort of easy and the other two were completely Chinese in a way. So I was wondering if you check some simple statistics just on the raw data, like if there's just, because you see all the models sort of stagnating at 60%, and I was wondering if 40% just doesn't contain any full words, or only contains a lot of numbers and abbreviations, or if there's some sort of a logic that makes you think if the input is just too bad, to make anything of.
We have to do those checks. I agree. We haven't done. For example, now that we have for sheet 1 the labels, we could see where the errors are, and we can try to figure out where the most of the mistakes are. And yes, I sometimes for example, as I mentioned, some of the information is proprietary, and that's where the ChatGPT is known to. For example, if there's a flavor code 19234 something, and then ChatGPT predicts the CPC code is 19234, despite giving the key value pairs of actual CPC codes. So it picks up the flavor code from the description. So there are known errors, and there are some unknown unknowns that we haven't yet delved into, but perhaps, that can be looked upon to further improve it, apart from prompt engineering. Yes.
Cool. Thanks.
Sorry,
Sarko, you're on mute.
I'm muted. Apologies. Oh, one more question from Peter. Go ahead.
So you said you process abbreviations in a step beforehand.
Yep.
Would you also be able to if the client provides it, go through these proprietary codes, for example, and
Yeah, can you please repeat? Sorry.
If the client provides more information on these proprietary codes, for example, you would also be able to process those, right?
Yeah, that would be helpful. We asked for it, but unfortunately, they also don't seem to have it. And I tried to Google them, and there are product codes that I could not find elsewhere on the internet. So yeah, perhaps if we can have it, then that would be great.
Super cool. Well, once more, very impressive data team. I think you did a lot of work over this meantime, and the results show. But this also makes me excited for the next presentation. So I'm curious to hear for the zero-shot learning.
Excellent. So I'm Justin Zarp, and Freek is also going to be presenting part of the presentation. Theodora, Freek, and I developed some of the notebooks, and there's also Yehia and Dennis who are also active in the team. A little recap of the goals that the data enrichment team mentioned. We want, as a zero-shot team specifically, to classify the client text without changing it. So all the projects happen in parallel, and our objective was to find out how far we could get with just the language models, without any data enrichment. So, and then as the project developed, the feedback from Metabolic was, yes, it would be really great to know the confidence level of the matched label, and also to have a few alternative options. What we more or less could expect, knowing what we know about language models, is that success depends on the model's ability to match client texts to the categories. So its internal understanding of the text that it's fed and the text that it's trying to match. And also, models are designed to guess the next word. So by definition, in the way they work, they're not very good at assessing their own work. And also translating and classifying in a single step could lead to also losses in accuracy. So this is kind of something we had in mind. when we started the challenge, and a little bit of definitions because we tested a few different metrics. So hopefully this slide clarifies everything. Yeah, using the tomato example, the tomato would be the client text, and the matching CPC code, which is the target, is tomatoes. We use this to validate our results. The full code is what we would call the 5-digit code, and the level 1 code is the first digit of these 5 digits. So it's 1 out of 10 classes. And top K would be 1 out of several, the top matches corresponding to the client text. And yeah, so sometimes we use different metrics on various experiments. Sometimes we use the same one, sometimes added, but basically they're summarized here. Exact match, correctly guess level 1 code. Level 1 code is among the top 6 matches, and a partial match. So not a full match, but an exact partial match. And we explore 2 different directions. The first being prompting, which was using a conversational large language model. And to do this, we wrote a description of the task. We explained how we would like the output to be formatted, gave an example, and then fed it the text and as a loop, and then reformatted the output as a table. The second approach is exactly what the data enrichment team did, was embeddings. And this was simply looking at the cosine similarity between the CPC classes and the client text. And here are some of our struggles. Yeah, with prompting, as everyone's mentioned already, the performance depends on task description. So there's always a little bit of uncertainty whether we have the most accurate prompt. We made 2 iterations, and we're able to improve the score. So at least we have a direction in which prompting works better. Yeah, another issue is the potential to generate imaginary classes and self-evaluation. This is something LLMs aren't good at doing in a single step. It's possible to ask an LLM to evaluate the answer of a previous LLM, but we didn't go into that. And the final limitation, which actually stopped us from exploring this further, was the context window size. So if we tried to ask the LLM to match a client text to all of the CPC codes, there'd just be too much text in the prompt for the LLM to handle. And this was at the point in our process where we decided to switch to embeddings, actually, so which gives a nice comparison. Now, talking about embeddings, the client text isn't always similar enough to the corresponding class embedding. And it doesn't account for hierarchical relationships. So we noticed also this by comparing 2 different approaches. In one approach, we tried to match only the level 1 embeddings, and in the second approach, we tried to match all the CPC codes. And the second approach worked better because a piece of, there's much more likely to be a direct match somewhere in this hierarchical structure than for a very detailed item to match the level 1 title. Yeah, and of course, this is a nice segue. So it might have made sense for the data enrichment team to go after us, but you've already seen that. Yeah, they've done some great work. Right, I'll hand over to Frank here.
Yes, thank you, Justin. Maybe if you can click a couple of times, I think it's animated. Yes, it's easier to show it like that. So the first approach is the prompting approach, and we'll just quickly explain how this method works. So what we did from the left side, we took the CPC taxonomy and we captured part of this taxonomy because of the context window size. We couldn't fit all the taxonomy in there, but part of it, we fed it into a prompt. We gave it the prompt some instructions to show how to format it. And in the end, we tried to output it as a table, but we figured out that actually JSON works better in the end. So it can really, the prompting can really make sure that ChatGPT outputs valid JSON, which we could parse. So that's very nice. And then combined with the product labels, we also fed them into the prompt. So you could imagine we made a list of 10 or 50 products, and then we asked ChatGPT, okay, can you match them to the correct place in the taxonomy? And that worked pretty well, but as I said before, it is very limited to a specific part in the taxonomy because we couldn't fit all of that into the prompt. So that's why we went for the next option, which is the embedding approach. And the cool thing here is that we use embeddings, and finding the differences between embeddings is something you can do fairly easy in a vector store. So here we took the complete CPC taxonomy. We made for every line in taxonomy an embedding, and these are in this figure the dense vectors. And then we saved them in a vector store database. And we did the same thing with the products that we had to classify. So we created embedding of them. And then in this vector store, we could find, okay, which products are very close to which taxonomy lines by simply using cosine similarity. So trying to find in this vector space which vectors are close. And then for every product, we could output 6 matches. And then with these 6 matches, we could, of course, simply pick the first match and say, okay, this is the best one. But we also tried an approach to find a common denominator between these 6 matches. So really trying to find, okay, are these results, are they in line with each other? And maybe 2 of them are in a completely different branch of the taxonomy, and 4 are very close to each other. So we can discover these kind of patterns. And on the next slide, we have a bit more how that's we've done that. You can click a couple of times more. It's all animated. Yes. So you have an example for 3 matches. So what we did there was trying to find, okay, is there overlap between these codes? So you can see here the 2225 is actually available for the first 3 matches. So even though the first match we found there, the 22252 is not correct, we still could go up 1 level and still find relevant information there. And yeah, that's what I wanted to say about the common denominator, and I'm happy to give the word to Justin again to explain our results.
Yep, so onto the results. Here's a summary. Starting from the top, prompting CPC level 1. This was the first attempt, and again, we decided to look at the accuracy, well, the correctly guessed level 1 for each item. And for the first attempt, it was 55%. For the second attempt, with a bit more concise prompting, it was 64%. In the second attempt, we also asked ChatGPT to return the most likely 2 guesses, so first and second guess. And actually, there was a very high score for the correct guess among the top 2, which then interestingly, when we tried to do the same with level 2, so only feeding GPT the level 2 CPC codes, the distance between correct first guesses increased, but total number decreased. And that's as far as we were able to go, because already with level 3, the number of tokens would be exceeded. So maybe in the future, with a model with a larger token context window, it would be possible to try all the different CPC levels, but there is some potential. What I think is happening here is the language model maybe is better at interpreting the client text. It does some internal data augmentation somehow, or well, the architecture of the model is able to interpret it better than just a simple embedding cosine similarity. But this can be part of the discussion for the more experienced NLP practitioners. Yeah, this is then our embeddings. Our first embedding experiment was just comparing the simple embedding of each client text to the level 1 embeddings, so a 10-part classification with an accuracy of 41%. And the second attempt then was looking at all the CPC codes, and there we got an accuracy of 63%, which was yeah, so correct correct guess for level 1, 63%, which is roughly performed the same as GPT, but much lower exact code guess. So what Vivek showed earlier goes quite a way beyond this. So we learned a few lessons on the way. Prompting is not so efficient when you have so many classes, because you have this huge context window. So even if models would have a large context window, they normally charge by the context size, so it would be a more expensive option. There seems to be some built-in data enrichment. You could ask the model to think about the inputs in a certain way, and thereby doing some input data enrichment, but that's really black box. The context window I mentioned, and LLMs are not good at estimating their own performance as they generate answers, because they're just guessing the next word, so they cannot also at the same time guess the accuracy of that next word. Right, embeddings. We got better performance by trying to match the text to all the classes than just matching a client text to level 1. Averaging the more frequently occurring classes, so the common denominator approach that Frank mentioned, increases performance, or at least it increases the certainty of which of the top K results is most likely to be found. We also encountered a problem there that if level 1 isn't correctly guessed, then this approach doesn't add certainty. So it kind of helps with finding the subclass, but not the level. Level 1 is still the main challenge. And further results were, of course, achieved by the data augmentation team. Now, I don't want to get in trouble here because the numbers didn't exactly match what Vivek showed, and this is just a challenge of having different notebooks. But what I did was I took the feather file which he provided, which had the predictions from the data enrichment team, and just compared the same metrics for simple vector embeddings on the raw data and vector embeddings on the enriched data for level 1 and also the exact class. Now, and what looks funny to me on the slide is why this correctly predicted class is 33% when Vivek was showing some numbers in the 60s. So we need to check this. Apologies. But I thought it would be interesting to just show the raw data versus the data enrichment team to also give them credit to the work they put in and how important it is to have a data-centric approach. And that's the end of our presentation. Thank you very much.
Thanks so much, Justin and Freek. Cool. Again, a lot of work has been done here. Several different approaches of zero-shot learning, which is of course a wide field. So it's nice that you've been able with one team to approach it in some different manners. I already see one question coming up from Ben.
Hi. Yes. Maybe I missed it, but I was wondering how does this top K say coherence approach work? So what happens? I think on the slide it shows that if there is a common denominator, that's good. But how do you actually use it, and what happens if there is not really such a common denominator, or if the top K is very it's not coherent, say?
Sure. Yeah. So I think here it's illustrated with 3 matches. In our implementation, we did it with 6 matches. And then what we're trying to find is sort of a number of matches you want to find that overlap, basically. So if you would have 6 and 1 would be completely different, then we allow for 1 or maybe even 2 exceptions to see, okay, what kind of area are we looking at? So you can play around with how many exceptions you want, how many classes you want to ignore. And then for the classes that are close, you try to iterate upward. So first you're going to check the first 2 and you see, okay, how many matches does it have? And you go for the second, the third, the fourth, and then you see how many matches overlap until the point that you don't have enough exceptions anymore. So you can only have, for example, in our end implementation, 4 out of 6 through the line. So you just try to go as high as possible for these matches. Does it make sense?
Yeah, I think so. Yeah, thank you.
Yeah, go ahead.
Hi, I don't have a question, but have an observation that I also encountered kind of the similar embedding. While doing this embedding search, I found out that, for example, if you take all the embeddings of all the CPC codes in the official taxonomy, for example, the official taxonomy has embeddings for 1-digit CPC code till 5 digits, right? So there are different numbers. So if you put all of those into one embedding store, and then you try to do a similarity search, sometimes I observe that you get the most similarity search for an embedding that need not necessarily be a 5-digit one. So this is why I filtered only the 5-digit embeddings, and then I did the top K matches only on the 5-digit embeddings, so that it is easy to further generalize later on onto higher levels. So because sometimes for a given example, I was getting only 1, 2, 3 embedding as a top match, even though, for example, 1, 2, 3, 0, 1 could be a top match, for example. So just one observation. Maybe perhaps you can also try to recheck your performance metrics once if you filter down your embeddings only to 5-digit ones, maybe.
Yeah. After I saw what you did, so this happened, for context, quite late in the process. We had already done our embeddings approach, but when I saw it, I thought it was brilliant because, yeah, you're getting rid of all the noise and just trying to match the most detailed. Plus, the results would perform differently, which is why I chose not to do it. But the performance of our approach is just looking at all the CPC codes at once in the vector store. But yeah, the takeaway from observing the two of our results, I think this is, well, it's something that's worth trying, because then we could isolate the performance of raw data. So yeah, it could be a quick check. Yeah, good observation. Thanks.
Okay, cool. And also with an eye on the time. Oh, there's another question still. Did I see it? Yeah, Yuri, go ahead.
Yeah, and apologize, I'm joining late. So did you analyze the biggest error? What are the biggest sources of errors?
We looked at the mismatched titles, and mainly noticeable one to me was language. I kept looking at Kasseler. Kasseler is actually a type of German sausage, but the embeddings kept returning different types of fish products. So in that example, actually data enhancement would really help with the way the Wix team did it, with translating into English, expanding it into a sentence, and then taking keywords out of it. All this sort of wrangling really gets out maybe the better meaning. Yeah, and then things like taking only level 5 category. These are tricks that you just have to try out.
Okay, thanks guys for your presentation. Then for now, last but not least, I'd like to hear from the supervised learning team.
Okay, cool. Hey, so things and stuff. Structure of our presentation is, we're not going to go over too much of the context, but just what we were finding from a supervised learning perspective. We won't reiterate the problem anymore. We have a set of solution directions that we decided to explore, and then we got some results out of the back of that. The members on the right here are people that, if travel and like work schedules allowed, would probably be doing more of this presentation than me. But as it is, I wanted to say that a lot of this work is done by these people, and if they were available, they would actually be doing this presentation in various other spots. So there'll be parts where hopefully some of them have managed to make it off their planes, and they can interrupt or correct me if they are here and if I get some of their details wrong. So the parts that we were looking at was, we were obviously a supervised learning team. And the task was obviously to do some labeling using CPC codes. We discovered during the process, the early processes of doing the work, that a lot of the LLM methods, while not strictly supervised methods, started becoming more accepting of being handed training equivalent data sets than they were when we actually started. And so it became possible to do very large file uploads using these sort of chat interfaces and relatively sort of free tier kind of stuff. And so as a result, that sort of changed some of the work that we ended up delivering by the end of it. We've also done some more traditional sort of hierarchical classification work as well. So there's a blended approach between the two sets of solutions we're doing. But yeah, sorry for the zero shot team. We accidentally ended up in your field. Apologies. So the next part is we did generate, similar to how Vivek demonstrated earlier, we have a data pipeline that's probably a bit more rudimentary, but we did get a sort of solidified train and test split. So we generated a stratified set of samples off of the DS1 page from the Excel spreadsheet with some of the codes corrected for zeros and all that jazz, and split between the two. So we had titles and codes in different columns. But generally speaking, we did sort of take this as a, what can we hand these models as a training set, and then what can we verify out of them as a test holdout set. So this manifested itself in three sort of deliverable areas of work, I guess. Claude AI was a model that became available in Europe and the US, I think in week 4 of the program. GPT-4 and Code Interpreter came out maybe 2 or 3 weeks later. And then we have a hierarchical classification stream of work that we also did, which is LLM totally removed. The ways that we were approaching this was we thought if we could get different training sets loaded into these LLMs, then we can actually start doing more training test prompt engineering. So we didn't really vary too much our prompting mechanisms. We didn't play with embeddings at all. What we did was we tried to find ways of generating what would constitute a test file, loading that into whatever the interface was, and then having a holdout set and then doing a comparison between the two sets. And so for Claude, we did a mechanism where we did no file upload at all. We said, do you know what CPC is? Generate the CPC record for this prompt, this client text. Then we had another experiment where we said, here is examples of exactly what we want you to match. We would like you to generate the labels for this set of client text with the labels removed from that set of information, but known to us. And then the final one was, can we take a definition of the CPC text itself, load that in as a sort of pseudo training set, but realistically as a gigantic prompt. And then what do we get out as a train test split and what the accuracy is there. So that's where the work started. Then it got picked up and partially replicated in ChatGPT, Code Interpreter, and GPT-4. And then there's also a hierarchical classification set as well. So in the hierarchical classification approach, we take a totally LLM removed technique, and we say, can we get hierarchical definitions out of these labels? Can we say this should be in this set at the top level, then a hierarchical classification downwards through that set? The sort of work is all far more sort of notebook based. So there are notebooks that can be expanded and perused upon later, but the generic outcomes are sort of roughly this. Using hierarchical classification, there is so Henry, we've all been traveling and we've got a little bit disjointed about what so Henry led on the hierarchical classification part, and the outcome of that was a logic for measuring hierarchical precision recall and the F1 on the models. And this has the possibility to set up a minimum percentage value that a prediction must meet as a fallback mechanism. So it's able to say, if you don't get a match here, then drop back, and this one is more applicable. I think that's fair to say, Jean-Marie, I think you might be around. And then for ChatGPT-4, Yuri did a lot of work on that one to lead to an outcome that increased accuracy by about 10% on what was previously there. So I think that was a 40% increase, 10% on 40, Yuri, you reckoned? Seeing as you're here and are talking.
Yeah,
that
go ahead.
roughly correct?
Actually, 10% is, we also, I want to just add, we also have a method, which is what we originally planned to do, which is the supervised method, where we start with the same solution that all the other teams started with standard embeddings and cosine similarity. And then we fine tune the embeddings based on labeled examples. So we bring vectors that are labeled to be matched closer and separate them from random vectors. And that approach increased accuracy by about 10%. So not ChatGPT.
Okay.
I can't yet tell like how much ChatGPT is better or worse than Claude.
Sorry, that was my mistake, Yuri. We were assembling these slides from dispersed notes while people were flying around countries. So yeah, my bad on putting the slides together the wrong way around, Yuri. Apologies. So then Claude AI did 3 examples on that. So we did 3 experiments when we were going in a few shot mechanism using only sort of pretext prompting. It was highly prone to hallucination and confidently predicting labels that didn't exist. When we loaded up the train test split, so I think the volumes of records were something like 120 to 80, or I think we did a 20-80% split on the DS1 sheet. So that gives you some idea about how much data we were loading at each stage. I was amazed that when the training data set was loaded and then the test data set was loaded without labels, that it hit 80% accuracy according to the existing labels you already had. And then depending on Metabolic's freedom of using alternative labels, another 10% of them not only looked conceptually similar, but are valid CPC labels and accurate, except not the ones that Metabolic provided in its training set. So the train test approach of saying, stratifying the samples you've already labeled, uploading that into the system, and then giving it a bunch of text that's of a conceptually similar approach, leads to a very high accuracy at a relatively low level of effort. Then the final sort of tests we were doing were to do with, can we upload the whole CPC spec as a text file and stick that into the system and have it prompted from client texts. And in those client texts, we found that the tendency to hallucinate pairings when fed only the CPC definition as opposed to a train data set, it would be more prone to hallucinating non-existent title to code pairs, but the titles actually, when they're isolated out from the CPC code, they're actually relatively accurate themselves. So that may be an approach that can be used to build training data sets in the future. So if you have no data and the CPC code, you can upload that, generate a training data set off the back of that, and then use that as a secondary step in the train test split when you've got a decent training data set built up that Claude seems to like. Some of the problems that we discovered varied. One of the problems that Claude had is accessibility. So Claude was only available in the US and the UK for the first couple of weeks, and then it was rate limited by messages per day later. And despite applying about a month and a half ago for API keys, we haven't been issued any. So as a result, the scalability of Claude right now is questionable for you guys out in the Netherlands, because I think that's where Metabolic is. But eventually it will be better, I guess. So yeah, I'm sure there's ways around it and rates and stuff you can use. But yeah, that was the generic outcomes. So to sort of, oh no, going backwards. Yeah, that's roughly everything. There we go, 5 minutes over time. But I'll pause there and wait for questions. And yeah.
Thanks so much, Dave. I see Ben is already on it, so go ahead, Ben.
Hi, Ben.
Hi. Yeah, I think the Claude AI train test, the percentages are super high, and that would be incredible. But can you be sure that there is no information leakage between the train and test splits?
No, I can't.
No.
As in, did not expect to be handling LLMs in this, and I have no. I honestly don't fully understand the concept of data leakage. So the answer to your question is I can't be sure. I barely understand exactly what you're aiming for with that terminology. What I can say is that by following the process of stratification in Claude, I was not feeding it client text it had already seen before. If that's in the same ballpark as the usage of data leakage there, then maybe that helps.
Yeah, I guess it's hard to know whether if you feed it training data, well, you could say, well, I feed it training data first, and then later on I ask it questions. But then in a traditional model, you can be sure that it's not actually looking at the at the labels of the test data or whatever. But in this case, it might be that it's actually making use of data that it shouldn't be using, because you actually don't know what's happening in the background. So I'm not sure if this can be the case. I would have to take a look at your approach. But yeah, if it doesn't, then of course this is a incredible result. So yeah,
maybe I can shed a bit more context based on what I did see when I was doing the process. So if you want to go in to see what I was doing, because I realized access was hard, the conversations and files are copied verbatim into the GitLab directory. So you can see exactly what I fed it, the exact source files I fed it, and the exact conversational prompts I used in each session. Then when it's generating the large volume of returns off of the test data set, I've taken that data out of the chat and I've used Python in the notebook to compare the outcomes between the two. So hopefully this makes the entire process reproducible from other people's sides, which I'd like. Obviously, like, you can't reproduce the exact conversation, but at the same time, all the relevant information for the conversation is documented. The second part is one of the things that I spotted, which was a bit weird, is that we did do some tests where one of the things I test in the notebook is I say, here's the test data set. We know the training data set should have the same set of, sorry, other way around. Here is the training data set. Here is the test prompts without the labels. We know that we're looking for labels that are in the test training data set already. But what Claude came out with was weirdly relevant labels that were correct and exist in CPC that weren't in its test data training data set. So in that scenario, it will actually produce things that exist, but that I didn't hand it, which was super weird. And that was both of those, Peter and Ben, both of those were my faces too, and I didn't understand what was happening either. And I would love someone to go, it's obvious you're an idiot, you missed this. And I'm like, I'd love that. That would be actually a good outcome for me. That would be a good learning outcome for me, but I haven't spotted where I potentially did that yet. And if someone can pull that out for me, please, I would love that. It's probably something stupid I did, but so far we haven't managed to prove it. So that's why I said it. I'm using yes, sorry, Ben.
So just one addition, just to clarify, did you ever feed it the labels for the test data as well, but just told it not to take a look at it? Or did you do the performance, or did you measure the accuracy outside of ChatGPT, or was that part of the prompt? Say.
Sorry, can you rephrase that? I didn't fully follow it.
Yeah, sorry, it was a bit messy. Where did you also feed it the test texts and the associated labels, and then asked it to measure its own accuracy, say? Or did you take the labels that it predicted and you took it out of the clause, and then you did you measured the accuracy yourself?
I took the labels it predicted out of Claude, built a CSV file, did string pattern matching to see if they matched what I was expecting.
Interesting. Yeah. Well, that sounds promising. Yeah. Thanks for the answer.
So we wanted to actually do one more experiment, but I think Dave wasn't able to do it because Claude access is now more intermittent. We wanted, instead of providing it.
That was the one.
Oh yeah, and that. instead of providing a traditional 80-20 train test split, we want to give it basically slightly supervised set where you basically give examples on how to do the matching, and then see what results are going to be, because that will clearly, if that works, that clearly says that there is no data leakage, and Claude just learning, like all the other language models, they're learning how to. You basically give it a rule how to do the mapping, and it figures it out. Not necessarily memorizing the table.
Sorry. Hang on. Okay. So to answer Vivek's question, I don't believe it's possible to get access to an API for Claude right now at the level we're operating. They seem to have a very weird set of public rollout where you have to apply and then they maybe select you. And I applied twice through both my professional and a Fruit Punch account and never heard back from them. So unfortunately, I was limited fundamentally to not using the API, which frustrated me. But that was a side effect of running these experiments. So yeah, that's everything. And obviously, this is the big limitation of doing this approach is you have to have a label data set to start with, right? Like you have to put in effort to make that work, and that's not necessarily true of the other work. So that's another thing to bear in mind with struggles on this one. Jean-Marie, do you want to go over any more of, if you are still here, do you want to go over any more of the results of your hierarchical classifications? Because I feel like I definitely didn't do that as much justice as it needed. No? Okay.
Yes, I think you summarized it quite well. Just to add, the hierarchical effort that we put in was mostly to have a measure of how well the model understand the CPC tree, just to know when it make mistakes, how close are those mistakes from the actual label in the CPC taxonomy. So we created those metrics. So by using just the predictions, so it will potentially work with any model. You just input the prediction and it tells you how well it performed, taking into account the structure of the CPC tree. And also, when you made a prediction, you have the ability to tell you a threshold value. So if you want, for example, the model to be at least 40% sure that that is the correct label, you can establish that amount, and it will automatically go to all the parent labels until it finds the one on the tree that satisfies that threshold. So it starts with the lowest label and goes higher and higher until it matches the threshold.
Cool. Thanks so much, guys, for explaining your approaches. And also interesting that that's the only not LLM-based approach, which is still functional. So that's very nice. Peter, you still had a question.
Yeah, January, can you clarify how the threshold worked? Because I didn't follow that.
Oh, yes. For example, once you can tell the model to predict a text, and also tell the model to output the label that satisfies a threshold that you establish. For example, of course, this approach requires that you have the ability to obtain that percentage value. So for ChatGPT, it's not possible because you cannot obtain a reliable percentage value. But if you're working with embeddings, you can obtain that value, and if it doesn't satisfy, for for example, if you start with a level 5, that is like the approach that most of us have been working on. You start with the level 5 labels, and if on that label you don't find any label that satisfy at least X amount that you put in, then it goes higher in the tree until it finds one.
Thanks, clear.
Awesome. Well, thanks guys for presenting these results as well. Again, some impressive results. I think Metabolic will have a lot of work to go through as well on the GitLab pages, and then see what is useful for them. But I'm very sure that that there will be a lot of useful material in here, a lot of different approaches that you've used that they could reuse or improve upon. So I'm also very curious where you guys will end up. Please make sure to share with us in Slack once you've made an actual implementation. I think everybody here would love to hear about how their work ended up in your product. So is there also someone from Metabolic that would like to give a final word to the participants?
I could go. Yeah, I just want to say thank you all for your work. I'm really impressed by all the things that you have tried, and I mean, this is a very hard problem, and yeah, I'm just really impressed how you organized this. So thanks to Fruit Punch for that, and for all you, all of you to participate in this. We will definitely keep in touch and let you know how we will implement this, because we are definitely taking this forward and make use of it. So, performance-wise and how it will look like and stuff like that, I think there are many things that we can share about that. And really excited to work on that. So thanks for all your work, and hope to see you in the future. And again, thanks a lot.
Awesome. Yeah, just to round off, guys, also thanks to you, Metabolic. You were really involved in the challenge and were able to help us out a lot with its progress and with your support and questions. So that was very valuable, and also made sure that we ended up, they ended up, I should say, with these results. And then once more to all the participants, well, these types of challenges always, of the final presentations, always give me a bit of the warm, fuzzy feeling that all these people were able to put through for 10 weeks, put in all this effort, and actually end up with these types of amazing results. Every time I'm overly impressed, and nothing less holds for you guys as well. So thanks so much. I hope to see you all in the next challenge or in the next masterclass. Make sure that you're welcome on all of the next events that we're organizing. And that's the final time for me that I'm able to wish you guys within this challenge a very, very fruitful day.
Yes. Thanks, everyone, for your efforts. It was a pleasure working with you all.
Thanks, everyone. Great results.
Thanks, guys.
Bye-bye.
Bye.
Bye-bye. Thank you.
Ciao, ciao.
Thanks, guys.